rest of the people until we have one. How deadly they can be, that's just a fact of life. You can't prove to a kid how deadly a pistol is till they see somebody get their head blown off. So, if we look at Chapter 11, let's take a look at it, which is the basic stuff on earthquakes. That starts, let's see, page 429. There we go. And we go to the questions, start on page 485. And some of this stuff is somewhat dated. These are the problems I'd like you to do. Problems 1. 4, 5, 6, 9, 10. Let's do, these are all good questions. 10, 11, and 12, not 13. So we got 1, 2, 4, 5, 6, 9, 10, 11, and 12.
Number 2, you threw in number 2.
Nice one. Number 2. Oh, number 2 I circled, but I don't think you need to do 2. No, not. You don't have to do 2. That's pretty obvious if you just look at the chart there. Now, what I'm going to be giving you are the kinds of things, again, that are in addition to the basic stuff given in the text. And this is, a lot of this is going to be stuff you aren't going to see anywhere else because it's based on the what Dave Rogers wished they would have told me when I was in school. I went and took these courses in dynamics and soil dynamics, and we would come out of those courses like somebody walking out of having a frontal lobotomy. We would be shaking our heads going, I just heard a lecture that was an hour long, but I can't understand any of it. That's what happens when you start getting into dynamics. And the way to really learn dynamics is to take a structural modeling course. And fortunately, when I was at Berkeley, I minored in structures, and that's where I really started understanding dynamics, because I took a modeling course, and we made models and put them on shaking tables, and we shook them, and we flashed strobes at them, and that's when I learned what the fundamental period of vibration of a structure is and what 1 degree of freedom means and all these dynamic concepts. You can't learn those things looking at a chalkboard. You need to see them in 3 dimensions. So teaching channel hydraulics or structural dynamics, very, very difficult thing to do. And teaching probabilistic theory is a very difficult thing to do. We're going to get into a little bit of that, but I always had these structural engineers who were always the biggest bane in my life, who would call me up and say, just give me a magnitude and a distance. Well, that's a deterministic method, sir. That's not, we're using probabilistic analysis. Well, all my computer program will handle is a magnitude and a distance, so you give me a magnitude and a distance. You just decide what it's going to be. You're the geotech guy. Well, that isn't, you start trying to explain this to them, and it's like trying to teach a 3-year-old physics. They don't get it. Probabilistic assessment is like making a big beef stew. You have a big pot, you put all kinds of things in it. Little earthquakes that are close by, big earthquakes that are far away, and you mix it all up in the stew, and you find out what things are real important and what things aren't so important. What you find out is there's no such thing as designing a structure for one particular earthquake. The great thing about living in today's age with synthetic motions and with computers is that you can take any structure and load it with all different kinds of earthquakes from different directions, different modes, high vertical accelerations versus lateral, from different distances, long period motion versus short period motion. And what you'll find out is different parts of that structure are sensitive to different kinds of motions. So to think you're designing for one kind of motion means you don't know what you're doing. And you don't even belong in the room if you're that low on the mental totem pole. It's a lot more complicated than that. That's like, designing the Superdome in New Orleans for 150-mile-an-hour wind with nothing in the atmosphere except wind, no trees or anything. Or designing for a flood where there's no sediment in the river. That's just called a lack of realistic awareness. It's not that simple. It's more complicated. So there is always going to be some measure of professional judgment. And what you want to do is go talk to people who have good professional judgment. That's the secret to success in life. Work hard, make your boss look good, and be able to recognize BS when you see it. And go find someone who really knows what they're doing. It may not be your boss. It may be somewhere else you have to go. Earthquakes. Why should we be concerned about earthquakes? Well, we have 4 million of them every year. That's 11,000 earthquakes per day. It's a pretty common occurrence. In fact, last week we had some in Nebraska. Not supposed to have earthquakes in Nebraska. About 6,000 of those earthquakes are strong enough for people to notice. The other ones don't get noticed typically, except on seismographs. About 800 damaging earthquakes each year that are just in the magnitude 5 to 5.9 category. Damaging means it does property damage and or it injures or kills people. About 120 destructive earthquakes occur each year that are magnitude 6 to 6.9. Now you got to remember, this is a logarithmic scale. So a magnitude 5.7 is 250% bigger than a magnitude 5.5. Ooh, that doesn't compute with any of you. Because nowhere else in your life have you heard two numbers so similar that are so different. But a 5.7 versus a 5.5 is all about killing people. That's about where the threshold is when you start killing people. You get up to a 5.7, you're going to start killing people. So they sound real similar. 5.5, 5.7, 55 cents, 57 cents. What's the difference? That's not very much difference. In a logarithmic scale, it's a huge difference. As much difference as between girls and boys. Big difference. All right. So despite improved building codes, we have about 15,000 people a year that are killed. Now that's going up. That number is an old number. It doesn't include the Szechuan earthquake, which is going to bump the number up considerably, because that earthquake alone probably killed about 1 million people. In 1556, we had 830,000 people we know were killed in Shenzhen, China, in one earthquake. 180,000 in Kansu in 1920. And you got to remember, there's a lot more people in China today than there were back in those days. But China and California are your earthquake leaders. They have the very, very complex and active tectonics. They're on active tectonic margins, and they got all sorts of geology that promotes site response problems, as we're going to see. 10,000 people killed in Mexico City in September 1985 in an earthquake that I studied in great detail. And that was by an earthquake that was 350 kilometers away. That was the deadliest earthquake the Western Hemisphere in the 20th century. and the earthquake came from the farthest distance away. How'd that? And that's the problem we have in the Midwest, is that same kind of earthquake. The people on the edge of Mexico City didn't even feel the earthquake that killed 10,000 people and injured 30,000. In 2008, 2003 alone, we had about 44,000 people that were killed, earthquakes worldwide. But geology beneath the site is just as important as the quake's magnitude. That's the point I want to get through to you today. So what is an earthquake? It's a sudden energy release. It's like an explosion. But the energy is in the form of waves, body waves. And we can measure those body waves with sensitive instruments. The place that plots on the Earth's surface above the focus, or the hypocenter, is called the epicenter. But the energy, this is where the rupture starts, and then that rupture travels up the fault plane, down the fault plane, and along the fault plane. So your proximity to where that fault scarp is on the ground surface is what's important, not your necessary proximity to the epicenter. That's one of the great dumb myths that's out there. Oh, I was only, 8 miles from the epicenter. Yeah, but you're parked right on the fault. That energy is going to come up the fault and then radiate away from the fault scarp. So the proximity to the epicenter can be a red herring. It's not necessarily controlling factor. It's your proximity to the surface expression of the causative fault that is more important. What does it look like when this happens? Well, here's a right lateral offset of a fence in Olema, California, that occurred in the great San Francisco earthquake of April 18th, 1906. And this particular offset is about 22 feet. That was not the maximum offset. The maximum offset was offshore, underwater, and it was probably about 26.5 feet, something like that, out west of the Golden Gate Bridge is now. So that you can see there, that's a pretty clean offset. That's a lot of energy being released in a very short period of time. Now that particular earthquake, moment magnitude about 7.8, it lasted about 43 seconds. The 1989 Loma Prieta earthquake, that particular quake, the maximum site response was about 15 seconds. And the maximum period of rupture was only 5.5 seconds. Very, very short duration earthquake. So when you see the T-shirt, it says, "I lived through the big one in 1989. That wasn't anything close to the big one. Foreshocks and aftershocks. You hear these terms bannered about. Foreshocks are not always diagnostic. They're not always consistent. The Chinese have done some really good work on looking at all this history of earthquakes and saying, before certain earthquakes we see chickens and dogs and different kinds of animals getting stirred up and agitated and doing funny things. And people used to laugh at that. They don't laugh at it anymore. But the Chinese will be the first ones to tell you that only occurs for about half the earthquakes. So there's some micro-fissuring that's occurring previous to a rupture. It's at the high frequency level that we can't sense, but some animals can sense it. But it's not consistent. It doesn't happen in every single event. It only happens about half the time. So that's not a reliable indicator of impending earthquake motion, but it certainly bears watching. Something that bears watching. Aftershocks are a bigger problem because aftershocks can knock structures down and kill victims who are wounded, and it can kill the responders, the emergency responders that are out there. So when you have damaged structures, one of the first things you have to do is to crib those structures or support them some way temporarily while you're getting people out of them. Because the structure's damaged, another smaller jolt can cause collapse. And aftershocks tend to decay logarithmically with time, but they can be some very, very large magnitude aftershocks when you have a big earthquake. The study of earthquake waves, or seismology, goes back the longest in China. China, we have the longest historical record. It goes back 2,000 years. Like our tsunami record in Japan, goes back 1,000 years. Seismographs are instruments that record these shock waves, and they can put those onto magnetic devices. This is like the basic Wood-Anderson seismograph developed by Harry Wood at Caltech. He was with the Smithsonian Institute out at California in Pasadena. And basically you have a suspended mass. You have these in 3 directions. We're just looking at the vertical direction right here. So if you have some sort of excitation in the Earth's crust, and you have to have this thing down on the Earth's crust, preferably on bedrock, as we're going to see, not on a soil site, and you're going to measure the vertical component of motion here, then you have another one in this direction measuring an east-west horizontal component, and another one in this direction measuring a north-south horizontal component. So you have to have 3 different instruments to measure 3-dimensionally what's going on. So seismographs, there's all different kinds of them. We start seeing them develop in the 1890s. There are different types of seismic waves. Surface waves, which travel on the outer part of the Earth, are the slowest ones. Those are the ones that get there last. Surface waves have very complex motions. They can also cause the greatest destruction, especially shear waves. Shear waves move back and forth like this, but the advancing front moves like my body, so like a sidewinder snake. And they create a lot of distress. And you can have different kinds of damage if they're propagating from the south versus propagating from the east or the west. You'll see different structures behave differently. That's because of asymmetry. If we take something like this, and we say if we have a building that's rectangularly shaped, and we have it shaped like this, and I have an earthquake wave coming from that direction at it, it's going to be very stiff opposed to that direction. But opposed to this direction, it's not very stiff. So when you have an earthquake in this country, and the Ozarks are a good place for this, the first thing you want to do is go out and look at the mobile homes. Because mobile homes look like this. They're very asymmetric. They're longer and stiffer in one direction than they are in the other direction. What you'll see, if the shock wave came from this direction, the mobile homes get knocked off their stands very, very easily in this direction, but not in this direction. You'll see tremendous asymmetry. Now, mobile homes are called Roman candles because when they get knocked off their stands, they pop the gas lines and they burn up like a Roman candle, 4th of July. They are very, very high risk for burning up and getting knocked off their stanchions. So you definitely want to spend the extra $150 if you live in a mobile home and you're in a seismic area. If you've got the mobile home parked on a floodplain in the Midwest, be sure and tie it down with some screw anchors and some cables. Doesn't cost much money. Costs more money to call an engineer and have him come out and say hi to you than it does to just tie the mobile home down. And put a flexible connection on the gas meter. Body waves travel through the Earth's interior. There's 2 types that we learn about in school. P waves, which are the compressional waves. P waves are what you see when you go out to an open pit mine and they do a load blast at lunchtime. And you see this wave shooting out like a torpedo explosion wake. And it comes up very fast and runs underneath you. And secondary waves are the ones I was just telling you about. Those are the ones that move at right angles to their direction of propagation. Those are the ones that do much, much more damage. And they travel only through solids. We don't get propagation of shear waves through water, because water has a Poisson's ratio of 0.5. So they don't travel through water, but the P waves generally travel about 1.7 times faster than the S waves. And the difference between these two is how we locate earthquakes. Secondary waves are slower. They have greater amplitude. And we also have horizontally propagating shear waves, and we have vertically propagating shear waves. Now, vertically propagating shear waves, the ones that come up from below and go like this as they come up, those are the ones that give us the most trouble for liquefaction. So for ground liquefaction, for lateral spreads, vertically propagating shear waves are our big enemy. And when we have an earthquake that's on a reverse fault or a thrust fault, like the Szechuan earthquake, wow, we see a lot of structural damage because we got big vertical loads. So we'll talk more about that. So what are the terms? I've already introduced some of these. The focus is the place within the Earth's crust where the earthquake wave originates. The epicenter is the projection of the focus up on the Earth's surface. And they locate epicenters based on the differences between the P and S wave arrivals. So 3 station recordings are a minimum needed to locate an epicenter. This used to all be done by hand. It's all done by computer today. In fact, there's 600 seismograph stations that you could dial into right now on the worldwide net. And if you can want to look at more of this on my website under geoforensics, there's a lecture on forensic geophysics, which talks about how we use these same principles to understand how large explosions are at different points around the globe. We just use the worldwide seismograph net to do that. So what you're doing here with a seismograph recording, and these are all done electronically today, is you're looking for the first P wave arrival and then the separation between that and the first S wave arrival. And then we see the big surface waves, big shear waves, back here. Now, these are 1 minute marks. So you can see here, we got 1 minute, 2 minute, 3 minute, 4 minutes, about 5 minute separation between the P and S wave arrival. And that's what we're going to use to get an idea how far away that particular earthquake was from where this instrument was. And so if we look at the relation between P-S wave interval and distance for the Earth's crust, the crust is the part we live in up on the top, we can see here at 5 minutes, that would equate to about 3,300 kilometers, 3,300 kilometers away. So that's about 2,000, a little over 2,000 miles away. So about from here to California. So if you have enough stations here, let's say we have a station in Paris up here, we got one in Montreal here, and we got one in Sao Paulo, Brazil right here. If we draw circles going out at that theoretical distances calculated for each one of those sites, where all 3 circles intersect is the epicenter area. And so that's what lets us know where the earthquake originated from in a very short period of time. We can calculate that. Now, realizing that, we look at 95% of the energy released by earthquakes are along very well described and recognized relatively narrow zones around the Earth. These are the earthquake belts around the Earth. The Pacific Rim of Fire, for instance. Magnitude scales were initially introduced in 1935 by Charles Richter at Caltech in Pasadena, simply so he could talk to the media about the relative scale and size of earthquakes. The Richter scale is not used anymore. The media still use the term all the time. We haven't used it in the scientific world for over 25 years. We use moment magnitude scale because the Richter scale is not an accurate portrayal above magnitude 6.4, and it doesn't mask out surface effects. So if you put a seismograph on a soil site overlying bedrock, it's going to overestimate the earthquake significantly because you're not masking out the site response. If you want the true energy release, then you have to use the moment magnitude scale. And I'll be giving you a handout on the moment magnitude scale next week so that you can have that in your engineer's notebook so that you don't use the word Richter scale. If you came out of my class and were one of my students, please do not use that term unless you're talking about it in a historical context. We don't use that anymore. You're just going to embarrass yourself. So, largest magnitude earthquake on the Richter scale, measured on a Wood-Anderson seismograph, was 8.9. That was the May 20th, 1960 Chilean earthquake. Magnitudes less than 2.0 are not felt by humans. And each unit of the Richter magnitude increases, a 10-fold increase in wave amplitude, and here's what I want you to know, a 32-fold energy increase. So when I go from magnitude 6 to magnitude 7, that's a 32 times jump in the size of the bomb. That's how you got to think about it, the size of the bomb, the energy release. It's a big, big change. So here, if we look in pounds of explosive, 1 pound of explosive for magnitude 0, magnitude 1. You look at here, this is how much it increases, and increases. 1,000 pounds of explosive for a magnitude 4. And then here you can actually see the 1946 Bikini atomic bomb test. That was about 20 kilotons for the first plutonium bomb. And then here's the Northridge earthquake in 94, Loma Prieta in 89, the 1906 San Francisco quake, and on down. Here's the Chilean earthquake, which up till December 26, 2004, was the largest earthquake in history. Now the Andaman Islands, Sumatra earthquake is of equal magnitude. That particular earthquake actually ruptured over 1,200 kilometers. So it was a bimodal. Peak ground accelerations weren't anything above like a 6.4. If you actually look at the earthquake and look at the peak ground movement, nothing bigger than a 6.4. The problem is it ruptured over such a long distance. The total energy release is way up there. So that's a nice chart to look at. Now, what are the different types of faults? The ones we hear the most about are strike-slip faults, because the San Andreas fault in California is a transform fault. It's like a stretch mark on a woman's stomach between two spreading centers, the East Mexico Rise and the Gorda Ridge, Mendocino Trench, and you have this transform between them. It's a rip, a tear. And so we talk a lot about that, but the earthquakes that really give us a lot of grief are these reverse fault type of quakes that have high vertical components on the up-thrown block, and a lot of highway bridges aren't designed for that. They're designed for lateral loads, and so we see a lot of failure modes up in these hanging wall blocks that that we didn't expect to see. We didn't design those bridges for. This was after the 1994 Northridge earthquake. So most of the bridge damage was up here on that block north of Northridge. If you're on the footwall block, typically don't see as bad of a problem. Normal faults are the kinds of faults we have out in places like Reno and Las Vegas and Salt Lake City in the basin and range. That's when we're in a tensile crustal environment. We have tension, we're pulling apart, and so we have dropping going on. And Dixie Valley, Nevada, they've had some whoppers out there, 1916, 1935, 1954. It's about 70 miles from east of Reno. And there they have these quakes that are along these normal faults where you have one side going up, the other side going down. The largest quakes in California are actually the East Sierra fault zone, which is one of these. And on that particular, in 1872, they had an earthquake in Lone Pine that was well over a magnitude 8. They actually get up into the high 8s. So they actually have to design dams and things on the east side of the Sierra for even higher loads than you would design a dam for in San Francisco or Los Angeles because of the proximity to the East Sierra fault zone. If we look, and again, here's again a nice semi-log plot. We're looking at earthquake magnitude down here versus energy release. And you can see here, here's the Bikini atomic bomb test, the 20 kiloton test. And then as we come up, these are different historic earthquakes going on up the line, and finally get to Chile way up here toward the upper end, which is in that one earthquake you had more energy release than the entire annual U.S. energy use in a whole year. Here's the Alaska earthquake, Good Friday earthquake, 1964. That's the March 25, 1964 earthquake. And that's really the humdinger in terms of, you go out and look at impacts of earthquakes, that earthquake, the shaking lasted 2 to 4 minutes, order of magnitude longer than the San Francisco earthquake, 1906, the Great San Francisco earthquake. And 400 Sturtstrom landslides, earthquake-induced landslides, involving more than 1 million cubic meters of rock. 400 of those. That's a lot of material. If that kind of an earthquake were to occur in the Pacific Northwest, where they had an earthquake just like that in December 1700, the damage to Seattle, Tacoma, Portland, you don't even want to think about it. You just want to stay here in Phelps County. Probably safer. It's going to be grim if they have a repeat of the 1700 earthquake, because they haven't been designing anything for earthquakes till just the last 15 years in Seattle, Tacoma, or Portland. They got unreinforced masonry on hydraulic fill all over those 3 cities. I mean, half of Portland and half of Seattle is on hydraulic fill. It's frightening. So is San Diego. Now, we go back and look historically. Here's the problem you have with natural hazards. What is that, Dave? The problem is everybody is only cognizant of the things they've experienced or heard about in their lifetime, which means they're not generally cognizant or worried about infrequent events, because infrequent events occur infrequently, right? So where's all the data? The data is all out in California. California is pretty much a post-World War II country, 5th largest economy in the world prior to 2008. Almost 40 million people. First building codes in the United States, Los Angeles. When? 1927. Why? Because of the 1906 earthquake and the 1933 Long Beach earthquake. After the Long Beach earthquake in 1933 down here, a magnitude 6.3 event, it knocked all the schools down. It would have killed all the kids in LA, just about, because they were unreinforced masonry, made out of brick. Looked like St. Louis. But the earthquake occurred in March at 6:15 p.m. The kids were home. So California passed mandatory laws at that point for structural engineering and for the design of stadiums, auditoriums, police stations, fire stations, and schools. And when I grew up, you never saw a brick building anywhere in the state of California, because brick basically got outlawed in March 1933, because so many of the brick buildings failed. And so they have a high awareness because they have many more frequent earthquakes along the San Andreas Rift. But the places that are really pregnant for disaster are here in the Midwest and in the Pacific Northwest, where they have very large earthquakes, but more infrequently than the smaller earthquakes they have in California. And it's hard to convince people that they need to do something about those quakes. They have had some big earthquakes in Charleston, too. One in 1886 and another one back in the 1600s. Well, engineering seismology is what I call this section, and it's the interplay between crustal motions and structural response. And this is the part that it took me so many years to properly appreciate, and so that's why I want to hit it with you. What are the mechanisms that commonly impact structures? There's surface fault rupture. We can understand that one pretty easily. There's ground waves and fling effects. I'm going to talk about what those are. Topographic enhancement of seismic energy. There's the dynamic consolidation of soils, which we don't talk about nearly enough because it's hard to get a handle on it and to predict it. Liquefaction and lateral spreading, site amplification, and long period motion, resonant frequency effects, and out-of-phase structural response. Now, I'm just going to briefly touch on what all these are. I didn't mention tsunamis, but tsunamis can kill hundreds of thousands of people when you have either underwater landslides or underwater fault rupture, surface fault rupture. There's 3 underwater landslides each day of the year for each above-ground landslide that gets noticed on the planet. So there's many more subaqueous landslides on the planet than any other kind of natural hazard. And they do cause tsunamis, frequent tsunamis, in places like Indonesia each year. So I'm not going to spend a lot of time talking about tsunamis, but tsunamis is a problem we haven't even begun to get our hands around until just lately, since the Sumatra Andaman Islands earthquake. And now when we look at old historic photographs in places like Los Angeles, lo and behold, what do we see? But huge areas of inundation, wave run-up strand lines running way past Santa Monica, all the way into the UCLA campus, that are prehistoric. Occurred hundreds of years ago. Ouch. And where do those come from? Well, from earthquakes up in the Pacific Northwest, probably, like the great December 1700 earthquake, big earthquakes down off Chile, earthquakes over in Japan. The way we discovered the December 1700 earthquake was the Japanese historic records on destructive tsunamis, which had killed thousands of Japanese. They looked at that one and they said, where did that one come from? And these tsunami modelers said, that came from the West Coast, North America. So then they started digging trenches over in Oregon and coastal Washington. Ba-boom, they found it. Place where the whole 200 meters of offset out in the ocean floor, and the whole coast came up a couple meters in one event. And whole areas that had been marshes were now dry and well above sea level. And when they started dating all of them, they all dated out right at 1700. All right. Surface fault rupture. Here's a sketch I made, a surface fault rupture. You have a fault, comes up somewhere, and it ruptures. And you also have these horsetailing, or these subsidiary faults that are tied to the main fault at depth. And these are what they've codified in California in something called the Alquist-Priolo Special Studies Zone Act back in 1972. But that's only about 2% of the earthquake-induced structural damage is surface fault offset. And you can actually design a structure to sit on a fault and rotate or hang together and not collapse. A Butler building, for instance, come out of Kansas City. You can have a fault run right underneath one of those things, and they have so many moment connections with all the screws and nuts and bolts that the building just gets kinked, turned, but it doesn't collapse and kill anybody. Virtually, the Butler building is about the safest thing you could be in an earthquake. We know that from looking at them at airports all over the world. Surface rupture is the one that gets photographed the most, because geologists can go out on field trips and they say, look at this. Rupture goes right across the road. And here's the scarp out in Dixie Valley. You know, look at that. Isn't that something? Isn't that impressive? Well, it's impressive, but it's limited in the extent of damage. You also have free boundary ground wave effects. This is the fling effect, where you have, if you look at the acceleration, that acceleration in the ground, you won't even feel it down here in a tunnel. You might get 0.05 G. But as you approach the free boundary, there's a fling effect. What happens is this thing goes nonlinear because you're no longer confined. And where you have an absolute lack of confinement, now you suddenly get some very, very high localized accelerations because of the sudden loss of confinement. You also have topographic effects. If you're on a steep-sided ridge, something that's 40 degrees or steeper, that's called the flagpole effect. This ridge is going to tend to oscillate and move much more violently in a given motion than down here in the bottom of the valley. In the Loma Prieta earthquake, at Corralitos, down here in the valley, we had a maximum peak ground acceleration of 0.77 G. That is a huge number. You don't design buildings for 0.77 G unless you're designing Hitler's bunker. It'd have to be something like that. But that was down here. When we went up and looked on the rooftops adjacent to Corralitos, on the ridge tops up here, we saw evidence of accelerations as high as 1.3 G. How do you know it's that high? Well, we had a concrete lid on water cisterns that was knocked off. When you look at the load on a concrete lid, concrete to concrete, you're going to have a friction of at least 0.3. And to take that whole thing weighing thousands of pounds and to shear it right off and dump it on the ground, that takes a big acceleration to do it. That's just basic statics. It's a big, big load. And those buildings were destroyed. We'd see all the buildings destroyed except we'd come along and there'd be one that would be sitting there just fine. So you go down in the county records, you look in the county records, and you find out, well, that one building that's hanging together was designed by a registered architect, and the architect went out and got a structural engineer and actually had some structural engineering, and they used tie-downs and a diaphragm roof, a few little extra dollars for a few little connecting parts. Buildings survived. The other structures were owner-builder, build them like they're down on the flatlands, no structural engineering, save $5, lost the whole house. Why? Connection details. Connection detail. The connection details that save a structure in a tornado or an earthquake shouldn't ever cost more than 0.5% to a maximum of 2% of the structural cost. That's what kind of peanuts we're talking about. So when you hear these people over in Tennessee and in Kentucky, and they're wailing like they've been diagnosed with AIDS, and they're telling you that to design for an earthquake is going to increase the cost of the structure by 100%. I've heard 400%. I've heard their state seismologists say that. That is a bunch of uninformed hype baloney. 400%? Nothing should make it cost 400% more. Heck, you can tear it down and build 4 of them for that cost. That's ridiculous. That's uninformed people trying to scare people and say, well, if you have earthquake codes, you're going to make it uneconomic for us to live here on the planet. No. There's 40 million people in California. They have earthquake codes in force there since 1934. It hasn't slowed it down too much yet. All right. Other topographic effects, ridge spreading. You take a big ridge in the Santa Cruz Mountains, you shake it a lot, and what's going to happen is it sags. Some of it goes this way, some of it goes that way, and you get soil-filled cavities, you get all sorts of grabens forming up here right in the tops of the ridges. So these tectonic processes leave fingerprints of past movements. And these kinds of finger or horse-tailing faults coming off the main fault aren't uncommon at all. If you have a major feature like the San Andreas, you're going to have all sorts of subsidiary faults rising off that main feature. And you're also going to see lurching. Lurching is movements of hillsides in response to long durations of movement. You just keep shaking this thing and shaking it and shaking it and shaking it. After you get past 4 or 5 equivalent cycles of loading, you're going to start seeing lurching. And a lot of that lurching depends on if there's pre-existing surfaces of slippage and how high the pore pressures are. It's all about the pore pressures reducing the effective stress. So lurching is where you have big portions of real estate that move in an earthquake. Really saw this in the Luzon earthquake in 1990. Saw entire mountainsides lurched, but generally only 1.5 meters. Not real far, but that's enough to take out your pipelines, your roads, and your anything else you have up there, your engineering infrastructure. So dynamic induced consolidation of fill is not lurching. What happens here is you have vertical component coming up, and you're causing consolidation, sudden dynamic consolidation of either valley fills or sidecast fills like this. And so you actually see movement afterward. This is very common with dams and with highways. In fact, the Chinese are collecting some great data on this right now on the Sichuan earthquake. They'll show you that every single one of the fills they had in those mountains on the hanging wall side has had substantive movement. Zipapu Dam settled 2.3 meters at one point in the middle of it. Should that surprise us? No, it shouldn't surprise us. The problem is we have buried utilities right here where you go from the bedrock to the fill. Your utility is going to snap right there because you have a catenary now. That buried utility is being stretched because the valley fill is settling. So you're going to have breakage somewhere across there with things like utilities. And then that creates more property damage. That's what happened in Oakland in 1989. They had a 8-foot diameter water trunk line that ruptured down up near the mouth of Lake Merritt. And it was the water coming out of that system under pressure that created all the property damage. Now, when you have highway embankments, especially fill embankments on approaches to viaducts like bridges, they're going to settle like this. You're going to have the center portion in compression, and the two sides are going to move out laterally. So all of a sudden, you might not have a highway that matches up with the bridge abutment, like this. This is one in Oakland that I was just talking about, right near the mouth of Lake Merritt. As soon as we got off the main span, I'm taking the picture from right here, we can see the part that's on the approach fill has settled substantially. In this case, about a foot, 12 inches. And the bridge itself is on piles. It's on a structural foundation. So the bridge can have some cracking and whatnot, but actually the bridge is pretty resilient if it's on bedrock. What the problem is, the things that are on fill are going to move around a lot. And again, if you have fiber optic lines or utilities coming through here, which they did in this case, right there is where they're going to snap. There's a big change in stiffness and support. So approach fills are the first thing you look at when you're going out and doing an earthquake reconnaissance. Find some bridges, look at the approach fills. You'll see right away how much trouble they had. Here's some approach fills that have been photographed in different quakes I've been to. Chi-Chi, Taiwan quake in '99. I can't remember one single approach fill we had in Taiwan where we didn't see something like this. I mean, they were just grievously damaged. And if they had embedded utilities through this thing, of course, the utilities were sheared. They were snapped. Here's another one. This is down in Chile, 1960 earthquake. And you can see where they had this entire embankment settled so much that the embedded caissons actually sheared and moved like that. You see a lot of these in Alaska, 1964. See right here, they're replacing it, approach fill with geofoam to bring the weight way down. Geofoam has a lot of great applications and things like this. If you look at the loads on pile groups, if you have piles like this supporting some sort of wing wall for a viaduct, and you have this whole thing move down, the load this is going to put, the lateral load it's going to put on these pile groups is huge. And you have to consider this in the design of it. This was a major problem on all the railroad bridges for the Alaska Railroad back up in 1964. And they just had failure after failure after failure where the pile groups got compromised. They got overloaded laterally. Settlement of approaches. There's what another picture of settlement of a viaduct approach. You can see here in this case, very, very grievous settlement of this approach fill reflected in the crib wall. And this is on caissons, the bridge itself, the main span, so it doesn't settle. Liquefaction creates a lot of bridge failures because if you have piles go down into something and that something, sands generally, liquefies, sands and silts, your bridge is going to go down. And that's pretty common anywhere you have a big riverine system with unconsolidated sands and you have more than 5 equivalent cycles of loading, you're going to see bridges go down. There's liquefaction and partial liquefaction of the foundation. Liquefaction looks like this. Sometimes you see the nice little boils. There's a textbook boil right there. Sometimes the boils are filled with fines, and most of the time what you actually see are these little ridges, these very, very linear ridges. These are tension fractures, especially parallel to levee dikes, and you just get this water that just came up and poured out of the ground. That's telling you had high pore pressures. Usually it's limited to the upper 50 feet. In the Midwest, we have evidence now of liquefaction going down to 70 plus feet, so quite a bit deeper. If we fly around New Madrid, Missouri, and we look, we see sand blows, look like baseball diamonds, about every 100 meters, and they're about 100 meters in diameter. But statistically, there's no larger field of sand blows in the world than that which we see in southeast Missouri from the 1811, 1812 earthquakes. You fly over it and you just see these sand blows. You can't even count them. There's just so many of them. And this is because they have channel sands overlain by lower permeability overbank silts. So if you have a pervious stratum like a gravel or a sand, and you have clay underneath it and clay or silt on top of it, that's the worst condition you can have, because you're going to trap the pore pressure until it comes up and ruptures through the low permeability material up on top, the lower permeability stuff, and that's when you get all these sand blows all over the place. So here's some down in Big Lake, Arkansas. And this is really pretty typical, where they run in linear patterns across the landscape. So they're really reflecting the underlying stratigraphy and showing you that you're having some big earthquakes in this area causing liquefaction over hundreds and hundreds of square miles. We can go out and look at some of these things like this. These are actually pictures right down here in southeast Missouri. We can go out and trench them and look at these sand dikes and gravel dikes. And then we try to take carbon samples, or whatever we can get, out of these dikes, and we date those. And when they dated them at this particular site, they found they had major earthquakes 1,450 years ago, 900 years ago, and 550 years ago, which probably were magnitude 7 plus events that occurred in the region. Paleo-liquefaction assessments are very valuable. If you do these different kinds of dating techniques at enough different sites, what you start seeing is these things line up. And these are 4 events. This is the 1811, 1812 event. This is an event around 1450, another event around 900 AD, and one around 500 AD. And so we got the last 4 events that clearly show themselves over a broad area, over many, many different sites. You can see there's about 25 sites there across the top. Now, what I want to introduce you to is a little bit about structural response and how that varies with the type of structure, what lies beneath it, and its location. Now, its location has to do with what's next to it, as you're going to see. You have the interplay of adjacent structures. Now, the first thing to remember about earthquakes is symmetrical is better. The more symmetrical you are, the less problem you're probably going to have in any given earthquake. Architects don't like symmetrical. Symmetrical is boring. Engineers like boring. That's why they became engineers. An unsymmetrical building would be something like this. An L-shaped building, and this is called a reentry. Now, the reentry is the first place I'm going to look to see after an earthquake whether I see any damage, because that's where the foci of any structural distress is going to generally be. Either here or where you have something heavy like a chimney or a stairwell or something on the end. But right there, what you'll very often see is where this building opened up and then closed back together. You'll see things like curtains or something coming out of it, that opening. So the framing tears typically at the reentry. If I have an earthquake wave train coming across here, like I show in the red arrow, this is going to tend to open up and rip open right here and then close back after the earthquake. So that's the first place I'm going to look to see how we did, see how this structure did. And that's the asymmetry in stiffness in this direction versus this direction. You see that? So, and again, it's like a dam. It's not the loading that comes from behind the dam that's the most grievous. It's the loading that comes upstream, because the dam's sitting there with all this big weight. Think of a big, huge Ozark boy who eats too much catfish, and you have this load coming at him, and that load's coming at him, and as it comes at him, the dam does this. It reacts inertially. So the earthquake hits it, and it's like knocking the legs out, and so the dam goes like this, But then it goes so far, and then its elasticity kicks in, and then it pulls back. And then it goes like this until it damps out the motion. And then the next wave comes in and hits it again. Now, if the next wave hits it, when it's already bent this direction, that's bad. Because now that's going to tend to accentuate it even more. And so you can get the structure getting plastic deformation at that point. Now let's look at a structure, look in the other direction now. We're looking at a high-rise next to a medium-rise building. Now the medium-rise building is going to have a different structural period than the big high-rise building. If this was built back before World War II, think of it like the constipated Irishman. The constipated Irishman is going to sit there, and it's a brick structure, and he's going to go, doesn't have much flexibility, doesn't want to move around, he's constipated. Whereas this one over here is like the Berkeley guy that's been smoking dope. He's loose and free, and he's moving around, man. And he's designed to move so that he doesn't get stress. If I strain, I shed the stress. So we call this a ductile moment frame building. It's designed to move around so it doesn't get cracked up. This one gets cracked up, but look what's going to happen on that one. So and this has a longer structural period, 0.1 seconds for every 1 story high. And then you have a natural period of vibration down here of the incoming seismic wave train, which depends on the depth and consistency of the foundation soils. So you have 3 different dynamic systems right here. If they get in sync with one another, you get what's called resonant frequency, and nothing saves the structure when you go into resonant frequency. You'll go from something that's going like this to something that's going like that, and down it comes. It collapses. Now, resonant frequency is much more common in a long earthquake, because each cycle of loading is going to damage this frame. And as the frame gets damaged, the natural frequency of the building gets retarded. So the building might start out at 1.8 seconds, 18-story building, but with each cycle of loading it goes to 1.85, 1.9, 1.95, 2.0, 2.05, 2.15, because it's getting more and more damage with each cycle of loading. So in the really big earthquakes, like Chile a couple years ago, you see these tall structures literally see their natural period degrade and get longer because of frame damage. We're designing the buildings not to come out of the earthquake without damage. That's not possible for big earthquakes. What we're designing them to do is not collapse for life safety. So we may get a building so damaged we have to tear it down. That's what happened to the building my wife used to work in, the Santa Clara County Civic Center building in San Jose, California. Its frame got damaged. They didn't realize this. It was getting damaged in earthquakes they had had along the Calaveras Fault in 1978 and then the Morgan Hill earthquake in 1984. So they had a series of 3 earthquakes. That frame got damaged. So when Loma Prieta earthquake came along, this big building, which was about 12, 14 stories high, the inside of that building looked like Bosnia, looked like a war. If there had been people in there, they would have been killed by the flying debris. What happened is the natural period of that structure had been degraded so much by structural damage to the frame from the previous earthquakes that when Loma Prieta earthquake came along, it was only 4 equivalent cycles of loading. Just nothing for a 6.9. 4 equivalent cycles, which you usually get on a magnitude 5.5 earthquake. But this one had high vertical shear waves, a shallow quake, and so that structure got going like this. And by the time they're on the last cycle, it was taking light fixtures and shooting them 35 feet across the room. So you look at the pictures in there, and if anybody had been in there, they would have been killed by all the flying debris in there. It was just trashed. But everybody had left early because the Oakland A's were playing the San Francisco Giants in the Bay Bridge World Series. So everybody was gone at 5:15 when that thing hit. Now, you can see the problem here. I have an earthquake wave front coming along here. The first cycle of loading, this is going to be the reaction. There's your big, fat Ozark boy. He's getting his feet cut off from under him, and by inertia, this mass is coming like that. And here's the constipated Irishman next to him getting a whole bunch of shear cracks. And everything's okay until we have the reaction cycle. Elasticity kicks in. Now the ductile moment frame swings back and crash. And all the California attorneys love it. Why? Whose fault is the damage to the little building? Well, of course, it's the big building. If he didn't have the big building next to him, he wouldn't have gotten crashed. Well, that's why they have to have codes in California that actually put a separation in between these buildings so they can't crash into one another. And you can't build a big ductile moment frame building right next door with a zero lot line with an unreinforced masonry building, because that's what's going to happen. One's going to clobber the other one, and you're going to have to tear this building down after the earthquake. And that happened in Oakland in 1989. They had a lot of building. Oakland, in fact, didn't recover from that earthquake for 10 years. Now, fundamental period of vibration of the structural components varies with their height and length. Okay, there's the constipated Irishman. Why?
Because it's so small and it's so stiff. When you get an earthquake, it's going to go, can't go anywhere.
But this guy over here, man, this guy says, no, you put him in an earthquake, he's going to go, Now, something's got to give between here and there. This is like parking a 5-story structure next to a quarter-story structure. They're not going to behave similarly. And this guy is going to get the big loads because he's so stiff. This is where the ripping apart is going to occur, is over here. This is nice and flexible. You're going to get a ball joint going here. You're going to get, this thing's just going to move. Now watch. Here's what happens. That's what happens in an earthquake. We got some big problems here. We're moving a whole bunch here, a little bit less there, almost none there, and these two snap. That's what happens. So when you have a freeway bridge, and you got a big long thing, you put all your attention into this, what breaks in the earthquake is that one. That's the one that breaks, because it's not flexible. You want to have flexibility in an earthquake. But if you put something that's flexible next to something that's not flexible, that's the worst possible thing you can do. So how do you solve something like this? That's not easy. One of the things you can do is you over-drill these. Bring them all down so they're all the same, close to the same length. Then the whole structure moves as a unit. It's not an easy thing to solve. All right. Now, what would be the seismic threat that we would pose to the St. Louis area if we had an earthquake that was a repeat of something like we saw in 1811, 1812? Now, in 1811, 1812, we had a series of 4 great earthquakes. 2 of them were on the same day, February 7th, 1812. But there were 5 events that were probably magnitude 7 or above, and there were about 2,000 aftershocks. These red dots are simply the earthquakes that have occurred in the New Madrid zone between 1974 and 1994, just a 20-year period. But what they do is they delineate the active fault zone for us. And we have a reverse fault called the Real Foot Rift here, and a right lateral transform fault that offsets along here. And so we have 2 different styles of earthquakes. The damage potential for these is tremendous, in part because we have 17 pipelines running up through this area that come from the Gulf of Mexico and Texas and bring oil and gas up into the northwest and the northeast. So these predictions are based on synthetic motion time histories with an assumed soil cover of 30 meters. That's not realistic, but it's a starting place. It's better than assuming the whole Midwest is underlain by rock, which it's not. Now, we have other seismic sources. If we look in the Midwest, we also have earthquakes in the Wabash Valley, which wasn't recognized officially as a seismic source until 1999, so just 10 years ago. And we have these other earthquakes that occur that are diffuse across southern Illinois. And they don't want to hear about those either. And when we go back and we look at using paleoseismology records, we started out calling these things magnitude 8, 7.8, 7.9. They've adjusted all of those down into these ranges now, the USGS. And these are very, very reasonable for the kinds of things we see described for the reasons I'm going to show to you. So our best estimate of the largest moment magnitude earthquake right now is magnitude 7.8. It's not an 8. And those are the numbers in the box that we're going to use. Now, shaking intensity, you got to realize, it varies from one area to another. And we call this seismic site response. So how much alluvium, the yellow stuff we have, beneath us makes a huge difference. If we're right here, or if we're right there, or if we're up on these hills over here, it makes a big difference. In Mexico City, the people on the hills right here didn't feel the earthquake that killed 10,000 people 3 miles away. They didn't feel it because it was long period motion coming from 350 kilometers away. It's coming out from the Pacific Ocean. Now, site response is taking this base motion down here in the bedrock and looking at how it's amplified as it comes up through these softer materials. Now, in the Midwest, we have nice, hard, unfractured bedrock. Paleozoic limestones, dolomites, and quartzites. The average shear wave velocity in this material blow your socks off. You're Californian. They can't believe the numbers. They still don't believe the numbers. 2,800, 2,600 meters per second. Way faster than a bullet coming out of an M16. What is the stuff up here in the valley bottoms, in the Missouri River, Mississippi River? About 180 meters per second. Okay, so it's more than an order of magnitude lower. Now what that means is this. That means for every second, I have about 15 times more energy here getting put into this alluvium than the alluvium can transmit in the same amount of time. So it's like taking a huge baseball bat on a little piece of chalk and just wailing on it. Because that energy can't propagate up through this as fast as it's being input by the bedrock. So when you have a Midwest earthquake of magnitude 5, it affects an area 20 times the size of the area that's affected in California. Because California is all busted up and fractured from being on an active continental tectonic margin. Back here, we're not on an active tectonic margin. It's very, very stable, unfractured basement for the most part. So you have entrapment of energy in here, and that's going to magnify the energy significantly. Now, that was the deadly combination we saw in Mexico City in 1985. We had a big volcanic basin that was filled with lacustrine clays in a big lake up almost a mile high around Mexico City. And when we look at the area that had the damage, here's where the people didn't even feel it. You can see the maximum peak ground acceleration, 0.035 G. That's 3,500ths. No, that's 35,000ths, actually, of a G. It's very, very low. And as you got out here, where they had about 30 meters to 45 meters of cover of the lacustrine lake clays, that was where all the death and destruction occurred. Every multi-story building, and all built with seismic codes, same as LA's, every multi-story building between 7 and 21 stories high was destroyed in that zone. That's why they had such high levels of fatalities. But it was just that narrow zone. And you can see in that zone, we went from 0.035 G to 0.14, 0.13 G. So we went up tremendously in the site response. If we look at the response spectra, what we see is here's the response spectra in G versus period, natural period. Here's the rock motion way down here, peaking at 1.5 seconds because the earthquake's so far away. Here's at 2 seconds, it's got a second peak, and then dropping off. And you can see here where you have 35 meters of cover, you have this huge amplification. And in Mexico City, we had one point between 30 and 45 meters. We had one point where we had 745% magnification. That was the biggest number in the world until I started working on St. Louis. Now, in St. Louis, at magnitude 6, from 224 kilometers plus away, I can get double that. I can get 1,300% magnification. That's the highest documented case in the literature in the world. Now, maybe Dave's full of bunk. Well, maybe I am. What's the first thing you do if you're a good scientist? You go back and you look at the records. And this is what St. Genevieve looked like in 1795 in a map made by Henry Victor Collot. And St. Genevieve is about halfway between St. Louis and the New Madrid fault zone in the upper Mississippi embayment. Now, they had had a big flood in 1785. And the town used to be right here, down here on the river. After they had that big flood, the town fathers, just after the end of the Revolutionary War, they wisely chose to rebuild the city up on the bluffs. Right here, excuse me, the old town was down here. They built the city on the Devonian age limestone bluffs, and they had no damage of any kind in the 1811-1812 earthquake, and all the three towns, the only three towns that existed downstream from them, Crothersville, Tiptonville, and New Madrid, were wiped out. They were on the alluvium. So being on the bedrock has historic precedence. It's a smart place to be. Well, here is looking at the Creve Coeur Bridge on Route D, and we're looking at an earthquake, in this particular case, from south central Illinois, a magnitude 6.8. We're not looking at magnitude 8 stuff. We're not looking at magnitude 7. 6.8, about the biggest thing we would expect out of south central Illinois. And you can see here the difference in the rock acceleration versus the soil acceleration right above it. And it's an order of magnitude difference. 0.13 G, 0.06 G maximum. So you're going to get a whole lot more energy being imparted to the bridge up here than you're going to have down here on the rock. Now the problem is this side of the bridge, just like the house I showed you, this isn't doing anything, and this one's moving like crazy. So you have a big problem. Now, if we actually look at these sites and look at the response spectra, now you get to see the impact of acceleration, of site amplification. You can see here, here's the rock record for that earthquake, and here's the site response. The site response is just frightening. They're huge, and they're very long period. What does that mean? That means they're 0.8 seconds and out further, which means that where the bridge is about 80 feet high, which is what it is, you're going to have way more loading on that site at 0.8 seconds. And for a structure that has a natural frequency period of vibration of 0.8 seconds, which this bridge does, it's really going to get loaded in a very severe way. So when you look at this ratio between this and that, that's the biggest variance we've ever seen looking anywhere in the world. So long period motion, long period structures are what's at greatest risk in the St. Louis metro area. Now, this is for the St. Louis metro area, and what I'm doing here is like we did for Mexico City. I'm showing you that for 21 meters of sediment cover, the red line, the bedrock's down here in the gray. You can see if you're on bedrock, most of St. Louis is less than 9 meters of cover. So most of St. Louis, you're fine. Stay away from the airport. The airport gets deep. The airport's about 21 meters cover. But as you get to the airport, now you're going to start seeing big changes. Now, as I get deeper and deeper, watch this peak. This peak starts moving and getting longer and longer and longer. Here's 38.5 meters cover, which is what you have underneath the main Mississippi River channel on the east side, like East St. Louis. Here's what you have at 28 meters and 35 meters, and so on. I mean, at 24.5 meters right here and 21 meters. So the deeper I get, the more amplification and the longer the site period. So that's going to affect tall structures or long structures. So here's a cartoon. The deeper alluvial cover, most of the Mississippi River is over 31 meters, and the Missouri River. That tends to magnify long period motions. So out here, it's not the shorter structures that are going to feel the excitement. It's any of the taller structures. When you get into the zone where you have less cover, like 18 meters, then it's the shorter structures. They're going to be much more vulnerable. And this is most of East St. Louis are these 3- and 4-story unreinforced masonry structures. They're going to be death traps. When you get into St. Louis itself, and you're very close to the bedrock, it's not a problem at all. Because like Washington University, or St. Louis University, you just don't have enough cover there. Most of St. Louis University's got like 9, 10 feet of cover on the bedrocks. Not enough to be worried about. We also have to look at modes of vibration. The fundamental or first mode of vibration is the one we usually look at, but we also have to consider the second mode of vibration if you're going to start looking at taller structures that are in sync. If they have the same period of vibration as the foundation has, then you can go into resonant frequency. So then you'd have to do a full-blown dynamic analysis and look at the frame and try to estimate how much frame damage you're going to have on each cycle of loading as well. It becomes a much more complex dynamics problem. So we have to look at site response versus structural response. And that's why it was so important for me when I was in school. I didn't really get this stuff figured out till I went over and took the structures courses. And yes, I had to get some B's to do that. Heaven forbid getting a B. That would be tough because I'm competing with structural engineers. But that's where I really learned stuff that was very important. You don't want to isolate yourself and say, well, I'm a geotechnical engineer and I don't need to know any structural engineering because it's too hard. Well, I got news for you. The hardest discussions you're going to have that I had in my career, they weren't with my clients. They were with my clients' structural engineers. Those guys will pick up the phone and ask you the hard questions. And if you don't know a lot of structural engineering, you're not going to be able to talk to them. And you're not going to be able to convince them of your point of view, especially if you're asking them to do something they haven't done before. They're going to be real hesitant and go, well, you're the only guy that's giving me those loads that are that big. You know, can you justify those? Well, it's pretty testy. So I was really glad I took those classes. But you learn about looking at this kind of dynamics and compare it to the dynamics on the site. That's very important. It's the interplay between those two things that knocks buildings down and kills people. All right. Other issues that structural engineers have to worry about are things like out-of-phase motion. Out-of-phase motion is the single biggest issue I get into on the various review panels I'm on for major structures like the Golden Gate Bridge. I was on the Bay Bridge review panel. I was on the Golden Gate Bridge review panel in the 90s. The problem we had was out-of-phase motion, the towers getting out of sync with one another. And that was always because of an earthquake 200 miles away. Long period motion is our biggest enemy on a flexible structure, like the Golden Gate Bridge. Not the 1906 earthquake, which is epicentered 9 miles away. It can handle that just fine. It's on bedrock. And all the bridges in the Midwest are on bedrock, the main spans. So we're going to see the problems, the tail spans. It's not the main span. Main spans are all on bedrock. They're going to do just fine. The problem is tail spans. So out of phase motion, you got to get into full-blown dynamic analysis, and you got to run earthquakes from enough different directions, enough different distances, enough different magnitudes, and enough different styles. And what you're going to find is Szechuan earthquake all over again. You're going to find it's the reverse fault that's going to give you the most grief. And that's what the Chinese are talking about right now. They're learning All the same kind of stuff they learned in California over the previous 25 years, which is our codes don't work because they were developed for strike-slip faults, and now we got movement on a reverse fault with very high vertical accelerations. That's why the dam settled so much. We're going to get a lot of great data out of that earthquake. So what are the future earthquake hazard maps going to look like after I'm dead and retired and gone from Rolla? This is what they're going to look like. They're going to look like spiders. Why? Because what's really important is the depth of the alluvium. So anywhere you have alluvium, there's the Gasconade River. Anywhere you have, actually that's the Merrimack, this is the Gasconade, and this is the Osage. Anywhere you have a lot of alluvium, that's the spot you're going to have the problems because of the enhancement of the seismic energy. So people always ask me in Rolla, should I have earthquake insurance? No, you don't need earthquake insurance in Rolla. Okay, Rolla's sitting right here. This is the Big Piney. We're right about there. This is the Merrimack. No, you don't have enough alluvium around here to have a problem. But the insurance companies, they don't like this map at all. Why? Well, because Rogers is going to tell all these people not to buy insurance and all these people not to buy insurance, and the only people buying insurance are going to be the high-risk people. And that goes against insurance theory. Insurance theory works on the principle of spread the load over as many people as possible. So I got paid $1,000 to come up and give this lecture at State Farm Insurance a couple years ago. I got a whole bunch of letters back afterwards saying, I wish you hadn't given us that lecture. Because that's not good news for us. What's going to happen is the federal government is going to get stuck with this. Because if these kind of maps come out and these people don't buy insurance, all the insurance burden is going to go on these people. And the feds will come in at some point and play socialism with you and say, well, we got to move this social burden over the whole country. So everywhere you live, you have risk of disasters. Or Rolla, you have risk of tornadoes, redneck attacks, and blah, blah, blah. And so they'll get you one way or another, probably. But that's where things are going to go. Because you can't keep this kind of information off the internet. It's going to get out there, and it's going to get to everybody, even on their iPhones. All right. If we look at the geology of the northern Mississippi embayment, and we cut across it, down below Cape Girardeau, so this is like looking at Poplar Bluff, coming on across to Reelfoot Lake. What you see is you have Crowley's Ridge in the middle, a structural high zone here. You have a soil-filled basin where the Mississippi River deposited this one, and the Ohio River deposited this one. This is Sykeston Ridge. And then you have more Ohio River sediments over here. So it's on these yellow areas that you got to be concerned, not on the bedrock. Now, if we look at the post-1812 seismicity, what do we see? There's a whole bunch of people out there right now telling everyone there's nothing to worry about because the crust is cooling. And so those earthquakes we had back in 1811, 1812, don't worry about it. They're not going to occur again. Well, there's a lot of people like hearing that news, I'll tell you. That's like me telling you, you know what, get rid of your car insurance. I think you're a great driver, and I don't think you're going to have an accident. Okay? What happens if the guy in front of you isn't such a good driver? What happens if the one next to you is drunk? Oh, well, you're dead. Is not having any insurance a good idea? I don't think so. What if the guy's wrong? Who's saying all this to everybody? He shows up at all these meetings to talk and give a counter to me all the time. And I'm always asking myself, who's paying for him to be here? He has unlimited availability to fly all over the country. Somebody's got to be paying for those flights. It's probably just because he likes to travel. Have we had earthquakes? Well, we had a magnitude 6.3 quake, Mark Tree, Arkansas, 1843. That's only 40 miles from Memphis. Memphis wasn't there then. Not much was there in Memphis. Certainly not a major city at that point. Magnitude 6.6 quake in Charleston, Missouri. That's the last big one we've had over magnitude 6. That was in Halloween 1895. Felt in 23 states. Magnitude 5.4 in Wabash Valley, 1968. That did some damage in St. Louis. Magnitude 5.0, Wabash Valley, 4.6 near Evansville, and 5.2 Mount Carmel. All those last four are in the Wabash Valley. We think that zone's capable of a magnitude 7 event every 1,000 years or so. So we have these paleo-liquefaction assessments that I showed you before. And we know there's been at least 5 events in the New Madrid zone. So what we do, we project those out. And we say, well, you know, there's something down here. Well, as engineers, we don't necessarily design for down here. We have to ask ourselves, you know, what kind of probability we want to design for? Well, the earthquake that's most probable in our lifetime is this one right in here, the magnitude 6 to 6.8 event. That's the one that's overdue if you just look at the data that's out there, collected over the last 200 years. So we don't have to just look at this one. You know, I have clients, you know, that say to me, well, you know, that's nice. I design things for 75 years. You're talking about a 500-year earthquake. You know, I don't cover that. That's what I have insurance for. Well, that's a valid point. You've got to learn how to answer that point when the client comes up with it. So the overdue event is this one. This is the one that's, you know, this one was due in 1985 through 2005. So it's 5 years overdue, way overdue, 25 to 5. And so that's the one you can't run away from as easily. So that's the one that I've been looking at modeling. So when I look at where these different earthquakes were, I actually end up concluding that there's 3 different source zones, and the magnitude 6 event is the one that's overdue. And so it has a 25% probability of occurrence in the next 25 years. Now, that doesn't sound like much if you're going to Vegas and you're gambling. 25% probability in 25 years with somebody who does probabilistic assessment is a huge, high probability. It's a very, very high probability. You got to realize that anything over 10% is a very extremely high probability. When you looking at the 75-year life. So 75-year life, there's a 75% probability you're going to have an earthquake in the time, the life of that structure. So that's a high number. You can't ignore it and blow it off. So either somebody has just done all the work wrong and there really isn't going to be any more earthquakes, you know, but that's a heck of a chance to take when you're talking life safety. That's what these codes are about. They're not about preventing the damage of the building and protecting the investment of the building. They're about life safety. It's about not killing people. How much chance do you want to take on not killing your kids? I don't want to take that chance. I don't have to take that chance. I don't want to take that chance. I mean, when I was in the Marine Corps, they gave us that one all the time. You know, I came into the Corps right at the end of the Vietnam War, and they tell you all these stories about young men, because young men are risk takers. You ever seen somebody driving like an idiot? It's usually male between ages 16 and 26, okay? You know, taking risks that are unnecessary. So you get young Marines. They've been out on patrol all day. They're hot. They're tired. The chow, a cold beer's waiting for them at camp over there. And here's a rice paddy. And they want to walk through the rice paddy so they can get to dinner 7 minutes earlier. But what's the rice paddy filled with? Water, bungee cords, mines, claymores, all kinds of things. Blow your legs off. Will the young Marines go right across the rice paddy? You betcha. You betcha. Why? Because they're stupid. We call that risk-taking, because stupid's not a kind thing to do. They're risk-takers. But do you want to take a risk you don't need to take? What about taking 7 extra minutes and going around and saving your legs from being blown off? Well, there's only a 1% probability my legs will get blown off. Yeah, what if you're the 1%? Will you regret that the rest of your life? Yeah, check. So that's the argument I use with people. You know, codes are there not to protect investments. That's a myth. Codes are there to save children who have no choice about where they're sleeping tonight, to save them from being killed. So once you see, you know, your first 25 dead kids, you'll get with the program. And that's what I always say about this guy who's my nemesis up in Chicago. I said, you know, they say, what's the difference between you and him? And I'll say, I'll tell you the difference between me and him. He hasn't been to 16 earthquakes and seen all the dead children that I've seen. Once you've seen enough dead children, you get on the program and you say, which side do I want to err on? I want to err on the side of safety. That's a no-brainer. If you don't have that much brains, you shouldn't be college. Okay. Last big earthquake, Charleston, Missouri, magnitude 6.6, probably closer to a 6.1 or a 6.2. Look at the area that's impacted. It's like 1/3 of the continental United States. It's like, wow. And that's theoretically an aftershock of the 1811, 1812 sequence. Okay, so if we take that earthquake, people felt it in 23 states. There was structural damage and liquefaction damage all up and down the Ohio River and the Mississippi River. And the longest iron or steel bridge in the world had just been completed 6 years before, the Illinois Central Bridge at Cairo across the lower Ohio River. And this bridge was damaged right here, where they went from the deck truss to the above deck Warren truss. And this got damaged in that, and this bridge was replaced in the 50s. But that tells you, again, that's a historic analog. It tells you, wow, that earthquake, epicentered over in Charleston and created all this damage, 35, 40 miles away. Now, here's the problem with the Midwest. Midwest quakes are less frequent, so they're not on the radar screen, but they're much more lethal. And the reason is attenuation. This is an attenuation plot. Down on the x-axis, it's distance from the fault in kilometers. And here's the modified Mercalli intensity. Here's California earthquakes. Now you got to realize California biases everything. Why? That's where seismographs were invented. That's where strong motion recorders or accelerographs were invented. That's where they have a lot more earthquakes. So all the data is biased to California. How much data do we have for Midwest earthquakes? DN squared, damn near nothing. So that's not too good. But the problem here is, when you get 200 kilometers away, you get about the same earthquake loading as you get at 300 kilometers away. That's why Midwest quakes are so deadly. We don't need as big an earthquake as California. We affect 20 times the area. So should we have codes that are more restrictive than California's? Yeah, unfortunately, we should. Got to remember, the exact same connection details you put in for transfer of shear in an earthquake are going to protect that structure from a tornado. Exact same stuff. It's not like it's a waste of time. It's called connection details. It's what you should be doing. It's like putting air in your tires and oil in your car engine. So we're going to do a probabilistic assessment. What are probabilistic assessments? They consider all the earthquake sources, all the magnitudes, the depths, the distances, and the probabilities. Now, probabilities, that's a tough one. If we want to know a 100-year flood, we need 1,000 years of record. If we want to know an earthquake that occurs every 1,000 years, like the magnitude 7 event on the Wabash Valley, we'd need to have 10,000 years of records. Now, we don't have anything close to that. What we have is 1974 to present, and some historic ones that we've gone out and done some paleoseismic work on. So we got a very, very small data pool, so we have a lot of uncertainty. And that's what the guy in Chicago is harping on. And when they ask me about that, I say, that's right. That's right. And from my point of view, the more uncertainty you have, the more conservative you have to be. Come on. That's a no-brainer. You don't have a lot of data. That doesn't mean you get to just skim along and say, well, it never happened. Never happened. Get your ass on an airplane and fly over down here and look at the place. Looks like a frickin' World War I battleground. You can't count how many soil sand blows there are. There's thousands upon 10,000s of sand blows. So you know that 200 years ago, the whole world came unglued down there. You know that. Are you going to talk yourself out of designing for that when it's 1/2 of 1% of the building cost? I mean, you need some mental help. You're talking yourself into that one. So very few engineers understand what's involved. They'll tell me, I want to design for a maximum credible earthquake. We don't design for maximum credible earthquakes. We do that using deterministic methods when we have nothing else. We have no earthquake data. We have no paleoseismic data. Then we drop kick and we use deterministic. And that's supposedly conservative. It's not always conservative if you ignore long period motion from earthquakes that are far away, which back here in the Midwest are very important. They're not important in California. So they're not in their protocol or in their doctrine. So we got to be careful about using Japanese protocol and doctrines or California protocol and doctrine. They are not appropriate back here. Because back here, you can get your ass blown off the building by something that's 350 kilometers away. That's not going to happen to you in California. In LA, earthquakes magnitude 8, 350 kilometers away, you're not going to feel it. Here, your building's going to get knocked down. We begin by running lots of synthetic quakes at the most probable sources and magnitudes. We look and see what types of motions affect our sites and our structures. We see what our structures and sites are most sensitive to. That's the logical way of progressing it. And I call this a screening analysis. It's an initial tool that lets me see what my site's most at risk for and what structures would be most at risk. The biggest problem I have in the St. Louis metro area is buried pipelines. Long, long continuous structures going across jello, then reaching the other side of the floodplain and going on to steel rock. How's that spaghetti line going to do in a big earthquake? Well, it's going to move around a lot. We should probably be building those things with a lot of flexibility in them, because that's a real tough one to make. The pipelines are going to break. And where are they going to break? Right at the edge of the floodplains. Where's all the material going to go? Into the rivers. Where does St. Louis and St. Charles get their water? Out of the river. How long can you live without water? Not very long. So for problem sites, you may have to use full-blown dynamic analyses with site-specific geotechnical data. That means you have to drill your own holes, get the data for that site, and run it. But typically you don't do that unless you go through a screening analysis and everything is bad. Then you spend the big money for doing the dynamic analysis. Why should we be concerned about old lakes and filled ground? Well, because the Mississippi River Valley is full of this kind of stuff. This is Callot's map, 1796. If we look over here, this is where downtown St. Louis is today. This is the Merrimack River coming in. Actually, that's the Merrimack River. I'm sorry. That's the Merrimack River. That's the Indian Salt Works on the cliffs above the Merrimack. And when we look over here, we see lakes. This lake is 8.5 miles long. There's lakes all over the place that are today filled in. And what do we have on those? Heavy industrial sites. If we go back and look at the 1908 Corps of Engineers maps alone, this is 100 years later, 110 years later, we can see some big lakes that were still there in 1908 that are no longer there today. Now, when we plot those and look at what's on top of them today, this is what we see. We see a highway network in here and interchanges crossing over these old lake features. And here's one, Interstate 255 and Illinois Route 3, that plot right over one of these old cutoff lakes at Bluff. So you have right here an interchange. This part of the interchange is on the lake. This part of the interchange is not on the lake, and that's something I'd be concerned about. Now, why? It's not, in so much of what we do in geological engineering, it's not about the maximum loading or the maximum strain. The problems in rock mechanics always get down to differential strain. If one half of your interchange is moving 16 inches and the other half's moving 6, you got a problem. If it were all on the lake, you'd be better off. If it was all off the lake, you'd be better off. But when you have half on and half off, and you got big bridges here, viaducts, big long continuous viaducts, those are very long period structures. When I take a shock wave and kick it through that thing, and it goes 4,000 feet up there and then comes back 4,000 feet, that takes a long time. That's a very long period structure. So it's going to be very sensitive to long period motion from an earthquake from a long distance away, 300 kilometers plus away, which is where the New Madrid zone is. North end of the New Madrid zone is about 225 kilometers to the south, and the south end of it's about 360. So it's definitely within range. So that could foster asymmetric site response problems. So asymmetric site response problems are really the biggest single thing we battle with highway and transportation infrastructure and pipelines, stuff like that. It's the asymmetry. So it's going from the fill to the bedrock that's the problem. Now, if we look at the Mississippi River floodplain, this is the digital elevation model. Check this out. There's Horseshoe Lake. That's one of the channels of the Mississippi River between Callot's map in 1796 and the Corps of Engineers map in 1908. Big, huge thing. It's a big state park now, filled with water. But look at all these channels over here and these old oxbows that have been filled in. Now, you talk about a heterogeneous environment. This is really wild. That's just looking at the surface. So when you go, you got to realize when you look at this valley fill in the Mississippi River here, and here's the Carondelet Narrows. Look at that narrow point right here compared to this big, broad area that's 8 miles across here at St. Louis. This is downtown St. Louis right here. When you look at this whole thing, what you realize is this is a very, very three-dimensional problem. You got to be looking at all of that stratigraphy because you have these channels, one over another, over another, over another. It's very serpentine. Well, what can we learn from modeling the impacts on some bridges? I took the 3 newest bridges in the area, and we looked at some different earthquakes. And we look at earthquake sources. We got magnitude 5 plus events at 115 kilometers, magnitude 6 plus events from 215 kilometers, and magnitude 5 at 223 kilometers. These are from the Creve Coeur Route D bridges. So I'm going to model New Madrid zone, Wabash zone, and South Central Illinois, all 3 of them. And I'll probably use I'm going to use a repeat of the Charleston earthquake of 1895, not the big, huge 1811, 1812. I'm looking at the most probable event. And so there's my 3 zones. I got the New Madrid zone down here. Here's St. Louis up here. I got the South Central Illinois zone, which they really don't like me. If I can't even give this lecture in Illinois without getting threats on my life. They do not like me using that term. That has not been officially recognized by the seismology profession. This one has, though. The reason is we can't look at these earthquakes. These earthquakes are down underneath the glacial drift. So they're occurring in the bedrock down beneath the drift, so you can't look at them like you can do trenches over in here and look at these, and do trenches in here and look at these at least and get some idea. You can't do paleoseismic work on these very easily. But there are earthquakes there. And you can see all the earthquakes on the drawing. So we have 3 different zones, and we have several different bridges. We have the Creve Coeur bridges, one across the Missouri and one across Creve Coeur Lake. And then we have the Herman Bridge site, which they haven't built a new bridge on. So if we look at the South Central Illinois, that's going to be 110 to 195 kilometers away. The Wabash Valley one at 195 to 275, and the New Madrid from 210 to 260 miles away, kilometers away. Sorry. So those are the distances we're going to be looking at. And what we're going to do is we're going to build artificial time histories using Dave Bohr's program. He's from U.S. Geological Survey out in Menlo Park, California. And we're going to look at the propagation of those through superficial materials using Park and Hashash's model there at the University of Illinois. And then we're going to try and predict, see how these things predict the peak horizontal ground acceleration, the response spectra, and the spectral amplification. And we're going to do a liquefaction screening using Yaud's methodology. came out in 2001. He used to be at the USGS, now then went to Brigham Young University on the faculty. So we developed artificial time histories for these different events, a mag 7.3, a 7.5, and a 6.6 at these different distances, and then applied those. There's the Missouri River Bridge on the Route D Page Avenue extension. You see the bridge is on the south side of the river. And here's what it looks like with vertical exaggeration. We're coming off bedrock on the south side, got the main channel here, and then we have this span coming all the way down to bedrock, and then these are on simply supported pile groups that go down into these channel sands, and we got these silts capping us right in here. And then the bridge slowly comes down. So this is like putting a 5-story structure next to a 7, next to a 9, next to an 11, next to a 13, and so on. So they're all different heights. The Creve Coeur extension bridge goes over Creve Coeur Lake. It has similar asymmetries coming off a bluff and dropping into the floodplain. Here's what it looks like. This very problematic. You're coming right off the bedrock on this one, and immediately this is like putting a 2-story structure next to a 12. And so you're going from very long to very short. So again, dynamically, that's quite a transition. And then you're getting out here and you're getting into deep pile-supported materials, very, very deep, almost 40 meters of sediment. So the Herman Bridge is the proposed replacement right here for the bridge that was completed in the late 20s. It looks like this. Herman's up here near where the Gasconade River comes into the Missouri River, about 50 miles upstream of St. Louis. Herman Bridge looks like this. Again, these are stylized with vertical exaggeration. But again, you're coming off bedrock on one end and then going into deeper and deeper sediments as you go out across the channel. Well, when we look at all these things and generate these artificial time histories, we used a number of different models. Everybody's model that was out there, basically, to model it. And when we did that, it's very, very interesting that what you see, these are bedrock time histories up here, that you see right there. And then what we find is, this is for the South Central Illinois event, mag 6.5, Wabash Valley, magnitude 6.5, and New Madrid, magnitude 6.5. Now what you see here is, this one's at 210 kilometers. You don't get nearly as much as you get out of this close one that's at 110 kilometers. So that one ends up controlling. So then we look at epicentral distance versus peak rock acceleration. We kind of expected to see these kind of things. They don't drop off very, very rapidly with distances. They're very nonlinear at distances greater than 200 kilometers when the magnitudes exceed 6.8. And that helps to explain the observations for the 1811, 1812 earthquakes. Why they got explained is everybody assumed they were so high. So what you're looking at here is magnitude 6, 6.3, 6.5, 6.8. I'm trying to bound the problem. So 6.8 down to 6.0. And then this is the deep soil program. We could model up to 23 layers of soil and do an equivalent linear approach with this. And there's various models that we have to use out there. This is Electric Power Research Institute. They're called generic modulus reduction curves. So we use those. And what do we find out is pretty interesting. If we actually look at these, this is the Creve Coeur Bridge, we see similar kinds of stuff where we have a bedrock motion down here, and then we get a bimodal amplification because this thing is reflecting off of itself. I mean, down here, look at this one. You're coming up here, we get a first exciting mode at about 0.35 seconds. And then we get a second one, which is right up around 0.9 seconds. And it's a very, very high amplification for the magnitude 6.0 event at 210 kilometers. And 6.3 event at 210 kilometers you can see very, very similar looking with a second peak on it. And the second peak, we didn't understand that early on, and that's actually because of resonance off the basement, because we're in a confined channel, bedrock channel. And so when we went through these things, we see very, very high load. This is at magnitude 6.0 to 6.8. And we say very, very small difference in attenuation between these. And so we have to look at this now and compare it with what's going on with the structure. If we look at an earthquake source, boom, we have an earthquake. The farther away I get from the earthquake, the more I see the fundamental period of that energy increase. So here it's very close, 0.3 seconds, 0.5, 0.7, 1, 1.2, 1.5, and so on. So the farther away I get from the earthquake, I call it long period motion if it's anything over 1 second. Now, when we design most structures, like in the Los Angeles or Bay Area, we're designing at 0.3 to 0.5 second periods. That's near field motion, because that's what you have in those kind of areas. It's not a problem out here at 1 second generally. Fundamental period versus structural height. So if we look at structural height here, we say the structure is 10 feet high, 20, 30, 40. This is the frame of the building. This is in meters, I'm sorry. This is in feet. Here we have the structural period. So you can see here, structural period 1 second when their structural height is about 60 feet high. And so this is of great import when we're evaluating structures that are more than 160 kilometers from the quake source. Now, here's what I want to get through to you. This is the real important slides. The fundamental period of a sand-filled bedrock channel, T sub S, is going to be 4 times the depth of the fill at that particular point divided by the shear wave velocity of this material, which most of the time is right around 180 meters per second, 165 to 180. Notice that I'm going to have a period right here that's not the same as here or there. And there's the problem. When you start putting something long across here, one part of it's going to be having a much longer period than the part that's back here. So your period's going to change at every spot. Your natural site period is different at every single spot from here out to there. Now, the Missouri River doesn't look this severe if you draw it to scale. I mean, it's only like 41 meters deep, and that's a couple miles out. So this looks worse than the problem actually is, except right in this area, which is where all the bridges are. All the bridges tend to be coming off the bluff and going to right about there at that point. All right. Impedance. What is impedance ratio? It's the ratio of the shear wave velocities in the foundation to what they are in the valley fill. So site amplification is a function of impedance ratio between the valley fill and the underlying basement. And the impedance ratios in Midwestern channels are among the most excessive examples identified anywhere in the world. So we take the density of the foundation times the shear wave velocity of the bedrock on top, and then the density of the valley fill times the shear wave velocity of the valley fill. You divide those two out, and the impedance ratio we have in the Midwest is horrid. Then we can estimate the shear wave velocity from the standard penetration test, corrected blow counts. I go through that thing. We don't have time to get into that in this course. I do talk about that more in 441. And we used Andrus's study because he's here in Charleston area and did his thesis under Ken Stokey. And when we look at these numbers, they're remarkably consistent at all sites throughout the Midwest, whether you're on the Illinois River, Missouri, Mississippi, or Ohio River, they all look the same. It's just incredible. I never expected that much uniformity. In the Midwest, all that matters is how deep I am in the ground. In California, the geologic age makes a huge difference. When you get back into the Pleistocene, you see a marked change because of calcification, because of carbonate cement. Makes a big, big difference on liquefaction susceptibility. But here in the Midwest, we don't see that at all. We have unconsolidated materials in the Midwest going back to the Cretaceous, which again, if you tell that to a person in California, they think you're on Mars. They go, that's impossible. And I get this stuff in my proposal reviews. That's impossible. You're crazy. Don't fund this idiot. He's nuts. Why? Well, because those guys haven't practiced back here. They all think I'm crazy. I am a little bit crazy. If we attempt to model a dynamic system, we have to be concerned about something called lateral incoherence. Now, this is really an important structural concept, and that's where I learned this stuff, was in structures. Okay? Lateral incoherence means if I take an earthquake load and I go bam, it takes time for that cycle of load to go through a long stretch of valley fill, or along a pipeline, or along a bridge, or up a structure and down. Now, up a structure and down a structure takes a few seconds. But it takes time. So you're not going to have maximum loading at every single spot along here at time t+1 or t+15. You're going to have pulses. You're going to be high, and then low, and then high, and then low, and then high and low. So you're going to have lateral and vertical incoherence, both in this direction and in this direction. And that's why the largest landslides don't just catastrophically take off in an earthquake. Think about it. The peak ground acceleration is coming up through that earthquake, and it's only up through that landslide. It's only loading one spot on the landslide at a given time. It's not loading the entire landslide simultaneously. So Newmark's method, as we're going to see in the next lecture, it only works for little bitty landslides. And statistically, it works great for little bitty landslides. Little bitty landslides don't do the big damage. It's the big ass landslides that do all the damage. And for them, you'll see them move a meter and a half. They don't just cascade off the mountain and run all over the place unless you get a Sturtstrom. And that's a whole different animal, as we talked about before. So you usually only consider lateral and vertical incoherence when you're doing a full-blown dynamic analysis. When you do a pseudostatic analysis, you're very conservative because you're ignoring lateral coherence. So the bigger a feature you're looking at, the more conservative you're getting. The smaller the feature is, the less conservative. So Newmark works great for little block slides about the size of this room. And that's what everybody uses it for and writes all these lofty papers about. And I'm sitting there going, oh, please. Well, that's nice. That's not the stuff that does $1 billion worth of damage. Okay. So artificial time histories, we looked at those. Here's some more of them for magnitude 6.8 to 8.6 quakes in the New Madrid zone. And now we're going back and we're actually trying to model 1811 and 1812 and compare them with the 1895 Charleston quake. So there's what the Charleston quake looks like compared to the big mama earthquakes that we have. These are your maximum event type things to your most probable events. So you can actually see, here's the most probable events looking like as compared. Now the big difference isn't not peak ground acceleration. The big difference is duration. And duration's a big issue if you're damaging the frame with every cycle of loading. That's going to become important. So these are for Herman. Same thing for the Herman Bridge. The Herman Bridge is much further away. It's 50 miles west. So you can see here. But you see the same kinds of relationships. Now, we looked at cyclic resistance ratio for looking at liquefaction. And we want to know how big of an earthquake do we need to start liquefying different layers in the Missouri River Channel, and how deep do we need to be worried? Well, this is 20 meters. That's 66 feet. So that's much deeper than anything we've seen in California. So this is a magnitude 7.3. We're having massive liquefaction at this zone, this zone, this zone, this zone. We've got 4 zones having liquefaction at that kind of magnitude event. Here's Page Avenue with an 1812 magnitude 7.5 event. Here's the factor of safety we like the design for. Here's a factor of safety of 1. You can see everything's liquefying out there in a 7.5 event. Well, that shouldn't surprise us too much. Here's a 7.5 event for the Page extension. Same kind of thing. We see the same 4 layers having trouble. And we go on through this analysis. And what we learn is, right there is about the threshold, 6.6. If we get 6.6 or greater, we're going to start having liquefaction problems. That's actually pretty good news, because that's on the upper end of our probability scheme. Here's a magnitude 6.8 event in south central Illinois, so that's closer. So now we're triggering quite a bit of liquefaction, all the way down to 19 meters, because the quake's closer to us. And here's magnitude 6.8 for a south central Illinois event on Page Missouri River Bridge. And this is where we would design for 1.15. And this is factor safety of 1. So we have zones that are just starting to go into liquefaction there. Same here with the, this is from Olney, Illinois. So this one's coming from the, a 6.8 event from the Wabash Valley seismic zone. So what does all this stuff tell us? Well, when we look at all these together, and we actually see we have a resonant frequency in the sediment pile in these river channels. So we're going to get one peak, then we're going to have another peak. This is very problematic for looking at long period structures like bridges. We can expect more magnification of spectral accelerations with weak ground motions, because these are less capable of triggering nonlinear effects when the soils go plastic. Once the soils liquefy, they're going to damp out further energy accumulation. So you get more magnification at magnitude 6 than you get at 6.4 or 6.8. Well, that's intuitive. We should understand that. The analyses suggest that long period motions, more than 1 second, emanating from magnitude 6.4 or less earthquakes tend to be most susceptible to this phenomena. So below 6.4, we're going to have a lot of magnification, but we may not necessarily get liquefaction. So what does all this mean? I'm going back on meet with the bridge engineers now. What does this mean? Well, it means I got to watch out for an asymmetric channel section. Mostly what I have on the Mississippi and Missouri River looks like this. What do you mean, Dave? What's asymmetric mean? It's not symmetrical. It means the river is way over here on one side, up against the bedrock. So I got this part of the bridge solidly on bedrock, this part's on bedrock, this main span goes to bedrock, but the tail spans are simply on pile groups. And these pile groups have different structural heights. Smaller, bigger, 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 as you come out on the tail spans. The soft pockets are the old oxbows out here. So when you're on, if you have these guys on an old oxbow, they're going to shake around quite a bit more than these guys over here that are in the sands. So you have widespread liquefaction hazard in these areas right here, where you have sands that are unconfined and are saturated. So that means you get something like this. You have simply supported tailspan zones. The magenta zones are the zones that are most ripe for liquefaction. So if you have this pile bent might do fine. This one might do pretty good. This one's going to do better because you have densification of the sands where you've been driving the piles. You see right here, this could be a big problem if this fails, or if this goes plastic, you could get some tilt of the structure. So your simply supported tail spans would appear to be the most vulnerable part of the existing long span highway bridge system. The site amplifications causing long period motions peak between 0.4 seconds and 1.6 seconds. So if this is 40 feet high, that's real bad. This one's 160 feet high, that's real bad. Well, you're going to have both of those. We can expect extensive liquefaction of foundations if we have magnitudes greater than 6.6. And that's toward the upper end of our probabilistic, most likely earthquake scenario. So what's our conclusions? We're going to get most of St. Louis is on 0 to 6 meters, so you don't need to buy earthquake insurance or get too excited. The problem is you're going to lose the firefighting capacity along where the fire mains are out near the Mississippi River, because that's the part that's going to liquefy. It's like it happened in San Francisco. Weakest link controls. You're going to have significant site amplification in the deep valley fills. Deep meaning over 100 feet thick, such as along the Merrimack River, the Missouri River, eastern side of the Mississippi River. Widespread liquefaction if you have more than 6.6 or greater, even at great range, even at 250 kilometers. Liquefaction likely continuous to depths of 40 feet in magnitude 7.5 plus events. All right, that's where I'm going to stop it today, because I think I've choked enough down your throats for one day, and I'll pick it up next week. Is this going slow enough that you're getting the concepts, or should I go slower than I'm going? You pretty much feel like you're understanding it? Okay. All right. Well, please read the chapter 11. Have any questions for me? I'll be around all week. And I'm going to cut it early today and stop now.